There we go. So today we're going to be focusing on section 8.4, at least the second half of it, because we already looked at multiplication a little bit last time. And we just barely started talking about division at the end of class yesterday. And I think that maybe when I introduced it in sort of a confusing way. So I want to back up and really make sure that we're clear on some of the notation for division. I've said in the past that math is a symbolic language. You sort of have to treat it like you're learning a foreign language because there's a lot of symbols that tell us to do or perform certain operations, and we have to be clear on what those symbols mean and what they are telling us to do. So some notation that you might be familiar with is that when you divide numbers, you can divide one number by another using the symbol our friendly neighborhood division symbol, right? This is the thing that we probably learned in grade school. And for maybe most of us that don't really deal with any other kind of math where we have to divide a lot of quantities in our lives or jobs, that is what you are used to. That is how you've always seen it. And maybe you don't know any other ways. But I sort of highly doubt that that's the only way that you've seen division, because you have technology. And when you divide in the calculator, sometimes it doesn't give you this symbol. So division can also be written. Obviously, if we had an example like 3 divided by 2, you could write it like this, and you would read it as 3 divided by 2. But for your keyboard on your computer, or like I said, on your calculator, even though you might have that division button right here, which you can't really see because it's sort of out of focus. Even though we have that button, if I were to type in 3 divided by 2, it shows up as a backslash. Okay, so you could also write division as 3 backslash 2. That means divide. And then in some software, some computer programming software languages, you might also see this written as a fraction, right? 3 over 2 can be interpreted as 3 divided by 2. And this is how we need to get used to seeing division written in this class and beyond. Okay, so it might look like a fraction, and you could read it as 3 over 2 and interpret it as a fraction, but you got to be flexible, being able to interpret it also as a division problem. Right? So it's both a fraction and a division problem, and we just have to get used to that. Okay, does anybody have any questions about that? Just how we write down division is what I'm getting at. Okay. And at the end of class last time, I said division is related to multiplication. And this is something that we probably intuitively understand, because, you know, if I had, let's say 21 divided by 7, that equals 3. And we sort of know that that's related to 3 times 7 is 21. So it's like reverse operations. So division is related to multiplication. If I could spell, which I can hardly spell and speak at the same time. Multiplication. And we can relate it this way. So if, for example, we had something like 5 times 3, if you have your times tables memorized, or if you wanted to do that repeated addition process, we could find the answer to that, and it should be 15. But if we have these two numbers multiplied to be 15, that also implies 2 other statements, right? That means that we know some relationship between 5 and 3 and 15. That 5 times 3 equals 15 tells us that 15 divided by 3 is equal to 5. Or it tells us that 15 divided by 5 is equal to 3. That's the relationship between those numbers. So at the end of class last time, I wrote something that might have been confusing for you guys if you're not used to variables, and we have to get used to them. But I said, let A, B, and X be real numbers. Okay. So when we have a division problem, we will see typically some number, let's go ahead and call it A, that's divided by another number, and we're going to use the fraction bar to imply that division. Okay. And that might be equal to some other number, some answer we might call X. If this is a true statement, if we've gone ahead and done the division and we got the correct answer, then we can check that answer because this statement implies that if I were to take the number that we got as a result and multiply it by this number in the denominator of the fraction in the bottom, that I should get the number on top of the fraction, right? That the division problem can be reversed into a multiplication problem. So X times B.
What do you mean by that?
We'll see here in a second. I'll give you another example where we actually look at some numbers. Okay, but whatever the number that we got as our answer for the division problem, if we can multiply it by this number at the bottom of the division problem that we call the divisor, that should equal the number on top. Okay. So has everybody written this down so far?
Yes.
Okay. Let's look at some concrete examples with some numbers, because again, it can be a little bit confusing or abstract when we just have symbols. So let's practice. Okay, so just as a reminder, if we have A divided by B, and it's written with the fraction bar as a fraction, remember in your head that that is equal to A divided by B, the number on top divided by the number on the bottom. Okay, so for our first example that we'll look at, we'll start off with something that hopefully is familiar. Okay, now I wrote this as a fraction, 36 over 9, but if I were to interpret this as a division problem, I would read it to myself.
So will it be 36 divided by 9?
Yeah.
Or 9 divided by 36, something like that?
So you have to be careful on the order. Okay, so remember that if I have this, it always will be the top number divided by the bottom number. Okay, if you change the order there, you'll land in a world of hurt. Like it's not going to work. You're not going to get the same answer.
Would it be in the negative area?
Well, no.
What happens if you get a negative number?
We'll get there in just a second. But let's go ahead and focus on this one, right? For now, we're dealing with these two positives. Okay, so let's go ahead and divide 36 divided by 9. What should that be?
4.
4, right? And you might know 4 right off the bat if you memorize your times tables, because remember, if this is the correct answer, it implies something about multiplication, right? If 36 divided by 9 is equal to 4, and if that is correct, then it implies that this number 4 times 9 should equal 36. And if these are true, if that's true, the multiplication part, then you correctly answered the division problem. Okay, so you could always check your division by reversing the operation and making sure that that multiplication works out. Okay. The other thing that you need to note, because we will see this, and we have seen some long division before, is that if we wanted to divide this using long division, then one helpful way you can remember how to set this up is that the number on top you could think of as the cowboy, and the number on bottom you could think of as the horse. I know it's very silly, a mnemonic device, but just go with me here. If we set up our long division, the cowboy sleeps inside, the horse sleeps outside. Okay. And is there anybody here that's a little bit fuzzy on long division, or we've done some long division in this class so far, but I haven't
The
really.
only thing I had trouble with when it comes to divide is showing the work.
Okay. So let me walk through this slowly, and hopefully we'll pick up that familiarity if you need to dust off the cobwebs with the long division. Okay. Okay, so with the long division, remember you're asking yourself 9 goes into 3 how many times? Well, it's too big, so we'll say it doesn't go in, it goes in 0 times. And then you ask yourself 9 goes into 36 how many times? And there you sort of have to count by 9s or multiply so that we get close to 36 without going over. Okay, so we would say like 9 times, maybe 2 is 18, that's too small. Times 3 is 27, too small. Times 4 is 36, so that perfectly fits. So we'll put a 4 here. Since 4 times 9 is 36, we'll subtract that because that's the way we've always been taught. And since we have 0 for our remainder, we can go ahead and stop or terminate that process, and our answer should just be 4. Okay. So just remember when you
So
set up,
0.4 or just 0.
no, there's no decimal in this one. It's just
Okay.
4. You could put 0.4, but it's simpler to just write it as 4.
Okay.
Okay. But remember when you set it up, the cowboy sleeps inside and the horse sleeps outside. Just so that we can relate that, because sometimes again, students will reverse the order here accidentally. And if you do that, you'll just get the wrong answer. Okay. All right, well, let's look at some other examples that are related, okay? And hopefully this clarifies some of the sign issues. So if I have negative 36 divided by 9, can anybody tell me what the answer to this should be?
-4.
Negative 4. Okay, and how do you know it's a negative 4?
Because there's only one negative sign.
Yeah. Yeah, that's right. But I think in your head, you either remember the negative positive rules for division from back in the day, or you're applying the multiplication sign rules. And it turns out that those rules are the same. So the sign rules for division are the same as multiplication. So if I have one negative number, or if I have different signs, a negative divided by a positive, different signs, then my result should be negative. Okay. But you should also make sure that that works in terms of multiplication. So remember that if this is correct, then it implies that this number, -4, that I got for my answer, times +9 should give me -36. And is that true? Well, yeah, based on what we did multiplying numbers yesterday, a negative times a positive is going to give us negative, and then 4 times 9 is 36, so we should have -36. That checks out, which means our division problem is correct. Does anybody have any questions there? Okay. Well, let's see if I can trip you guys up. What is 36 divided by -9?
Zero. Wait.
-4.
-4. Okay, and again, the sign rules for division are the same as multiplication. So if I have a positive divided by a negative, then I should get a negative because they're different signs. But again, we could say that this should be correct if I can take -4, multiply that by -9, and I should get +36. If that is true, then I did this division correctly. Well, a negative times a negative should be positive, because remember last time I said if I have two negative signs, that a pair of negative signs cancel out. And you could do like these visual tricks in your head where you say, okay, if I have one minus sign and then I have another one, you could sort of stick them together and get a positive sign. Okay. And that's just like a helpful reminder. Okay, but you should just remember that a negative times a negative should give us a positive. So if this is true, then we should have the correct answer for our division problem over here. Does anybody have any questions or comments here? Okay, moving on. Okay, one last flavor of this problem. -36 divided by -9 is equal to what?
+4.
+4. Okay, and the reason why that is, again, always go to the world of multiplication to sort of verify. If this is true, then that means that this number 4 times -9 should give us -36. We have a positive times a negative, and that is a negative, and that seems to be a true statement. So that means that our division problem was worked out correctly. Does anybody have any questions about those? Okay. Well, now let's examine some other problems using numbers different from 36 and 9. Okay. So let's go ahead and examine some things that give students a little bit of difficulty here sometimes. So let's examine the following examples. 0 divided by 10. Does anybody know what that is?
Would it be just
10.
10?
Would it be 10?
Yes.
Does anybody else have a guess?
0.
0. It should be 0. Okay. But let's think about why. Okay, remember that if we have this as a division problem, and if this is the correct answer, then that implies that 0 times 10 is equal to
Oh, makes sense now.
0. Is this correct?
Yes.
Yeah. We learned the multiplication rule by 0, right? Multiplying by 0 results in 0. So multiplication by 0 is 0. So if we can think about it in terms of multiplication, then the division problem becomes a little bit clearer. So here, we might then take our problem up a notch and say, okay, what is 0 divided by -3? What should that one be?
Still 0?
Yeah, still 0. And again, you could verify that, and you should verify it if it's still fuzzy, because this 0 times -3 should be 0. And if that is true, right, that this number times this one equals this one. If that's true, then the division problem is correct. And it is, right? 0 times even a negative number should be 0. Right? You might be tempted to put -0 if you're thinking about 0 as a positive. But the thing is that 0 is neither negative nor positive. 0 is its own opposite. I think we said that a few class periods ago. And so you don't have to put a negative sign in front of it. -0 is the same thing as 0. Okay. But in any case, what these two examples should establish for us is a general rule that 0 divided by anything is 0. Okay. But I don't want you to overgeneralize that. This is true for 0 divided by any number. Okay. Can anybody tell me what 20 divided by 0 is?
It should be 0.
That's actually not true.
Oh wait. It'd be 20?
Why do you think it's 20?
I don't know.
Right, so that's what I'm getting at. We sort of want to make sure that we're not guessing or overgeneralizing this, right? Because in these examples, the 0 was on top. So you can think of it as 0 divided by a number is always 0. That's always going to be true. But in this example, the 0 is on the bottom. So it's not the same kind of problem. This is 0, a number divided by 0. Do we have any other guesses for what this might be?
I mean, if you put in a calculator, it give you an error.
Yeah, it does give you an error, right? So if I put this in the calculator, 20 divided by 0, I get error, divide by 0. And you should be, in whatever calculator that you're using, you should be getting an error. And the reason why is because you cannot divide by 0. It is what we call undefined in mathematics. There is no definition for how to divide by 0. Okay, and this should make sense because let's say that, let me go ahead and
How is it undefined? Undefined?
undefined.
Undefined.
like
How is that undefined?
Okay, let me explain. So it is undefined because let's say that I had 20 divided by 0, right? And let's say that that is equal to some number x. I don't know what that number is, but let's say that there is an answer for it, and we'll just call it x. If I have that, then that implies, right? We can think about it as multiplication, that this number x times 0 is equal to 20, right? But a number times 0, is that ever going to be 20?
No.
Right, because something times 0 is always going to be 0. So this doesn't make any sense. So when you divide by 0, that leads us to nonsense. So that must mean that we can't divide by 0. So that's why we say it's undefined, because there's no definition for how to divide by the number 0. Okay, so we say division by 0 is undefined. Okay, and you can interpret this a couple of ways. You can say division by 0 is undefined. Another way of saying it is that you cannot divide by 0. Or you could say that we cannot have 0 in the bottom of a fraction. And again, just to sort of clarify that a little bit, let's say that, put a little box here, give me some working room. Let's say that, you were tempted to say 20 divided by 0 is equal to 0. If we said that, remember that implies that 0 times 0 is equal to 20. But that doesn't make any sense. And if you wanted to guess, let's say 20 divided by 0 should be equal to 20, then that would imply that 20 times 0 is equal to 20. And that also doesn't make any sense. You could guess any number here, and it always leads to nonsense. It sort of violates our rule for multiplying by 0. And that is a law. We cannot violate that. So whenever we have 0 in the bottom of our division problem, we just have to say our answer is undefined. Or sometimes you might say that there's no solution. Okay. Does anybody have any questions or comments there? So just be careful not to rush into things. Make sure that you read the division problem and you interpret it correctly, you slow down. Because you don't want to go and say like 0 divided by a number is undefined, because that's not true. And you certainly don't want to go say a number divided by 0 is 0, because that wouldn't be true. You don't want to mix up these ideas. Okay. Okay, well, so far we've been dealing with division problems that are purely using integers, that is using whole numbers. And clearly sometimes you will have to divide some numbers and you won't get a nice whole number. You might end up with a decimal. That decimal might be ugly. It might be what I call pretty or a terminating decimal. So let's review some or get some practice of dividing some numbers that don't give us a nice whole number answer. Okay, let's go ahead and practice. If I gave you the problem 25
I have a question.
divided by 4, yes?
Is there any practice that we could do on the math book just in case we need help with certain things?
I mean, the practice is what you would be getting in the practice part of Hawks, right? So it would be in the homework assignment.
No, I was talking about the math book that we got from the school, from the bookstore.
Yeah, I mean, you could go to the workbook that you got from the bookstore corresponds to the learn part of Hawks in your homework, right? So some of you might be completely ignoring the learn part, and that's fine. That is just there for extra help. So if you want to work out the problems in the workbook and those are giving you trouble, then just pop into the learn part of Hawks, and that should align with what is in your workbook. Okay, but again, that is just if you want extra practice. I'm giving you what I think you need, so I don't really lean on the workbook.
So what's the point of having the book from the bookstore?
That's a good question, and it's a discussion that is not related to right now. So if you want to talk about that after class, we totally can.
Okay.
Okay. Okay, so let's jump into some practice with division, right? Let's go ahead and can anybody tell me what should I get when I divide 25 by 4? And remember, we want a decimal answer.
6.25.
Yeah, and how did you do that?
I guessed.
Did you guess or did you put it in the calculator?
First I guessed, and then I double checked my answer with the calculator.
Okay. So we want to make sure that we're doing this by hand just so that we polish off those skills, right? We don't want to be using the calculator too much as a crutch because there are some of these things that we should be able to sort of whip through by hand and then we just lean on the calculator when we get to more complicated, longer problems, right? But for now, I really want you to emphasize trying to do this by hand. Well, how would you do it by hand? Well, the way you would do that is long division. So remember, we could think about this as the cowboy rides the horse. So the cowboy sleeps inside and the horse sleeps outside. Okay. We could do 4 goes into 2, 0 times. 4 goes into 25, 6 times. And then you have to remember 6 times 4 is 24. And we get a remainder of 1. But we want a decimal answer. So if we want a decimal answer, what we can do is just throw a decimal here and here. And we can throw as many zeros as we need to complete this problem, okay, behind that decimal place. Right, because 25 is the same thing as 25.0. There's no difference in those values. So we can add as many decimals, any zeros behind the decimal place as we need to. So we'll drop this 0. And then we'll ask ourselves, can 4 go into 10 now? Okay, so 4 goes into 10 twice. 2 times 4 is 8. We can subtract that, get a 2. But we still have a remainder. So let's go ahead and throw another 0 in the mix. We'll drop down that 0. And now we can ask ourselves, does 4 go into 20? Well, it goes in 5 times. 5 times 4 is 20. And you can see that we don't have any remainder there. So that ends or terminates the process. So based on that work with the long division, we should be getting that 25 over 4 is equal to 6.25. Okay, and that's an exact answer. But typically in a lot of the homework problems, they might ask you to round your answer to estimate something that's close to your answer. So let's say that we want to round our answer to the nearest.
Can you scroll it up a little bit? Thank you.
We want to round our answer to the nearest 10th place. 10th place. So how would we take $6.25, and round it to the nearest 10th place?
If you're rounding the nearest 10th place, will you go to the right?
Yeah.
When you do that?
Yeah, you would. So this is the 10th place. So if I'm rounding to that place value, what should this be approximately equal to? What does this round to?
I'm gonna assume it's gonna be 6.2.
Not quite. So it turns out that we can look at the place value next to the 10th place, and it's a 5. And usually 5 and up is our cutoff that we say, okay, if it's a 5 or more in the neighbor, then we can bump this number up by 1. So we would say, okay, we'll call this a 6.3. And that is going to be our approximate answer or a rounded answer, where this squiggly equal sign means approximately equal. Okay. But clearly we need a little bit of help or a little bit of a reminder of how to round, and in order to do that, we sort of need to know our place values. Okay, because they might say round to the nearest thousandth place. And you need to know what decimal value are they talking about when they say the thousandths or the hundredths. Okay. So let me go ahead and let's go ahead and think about our decimal number system for a second. So we have a decimal number system that is, sometimes that's referred to as base 10. And the reason why we call it base 10 is because we have these place values in our digits for our numbers, and each of them can store 10 values, 0 through 9. If we get more than 9 in a particular place value, then we have to sort of pour that over into the next place value up. But if I were to give you a number like, let's say 7,324.079, you could read this as 7,324 point, or you could say, and this is the tenths, hundreds, thousandths, so you could say 79 thousandths. Okay, but we have place values, right? You can think of them as little slots where these numbers go, or these digits go. And they each have names, and there's more slots still to the left and the right, you know, if we have a bigger or a smaller number. So we should know that the place value next to the, on the left side of the decimal is the ones place. Then comes the tens place, the hundreds, then the thousands, okay. Then after that comes the 10,000s and the
And so on.
and the 100,000s and so on, right? Right. Then you go into the millions, the 10 millions, the 100 millions, then the billions, right? And it can grow from there. On the right-hand side of our decimal place, this is where I think students have a little bit more fuzziness, because when we're dealing with money in our actual lives out there in the real world, we usually only go out to 2 decimal places.
That
These are-
messes me up all the time. On
Yeah,
the left-hand side?
over here,
Yes.
the right-hand side.
Yeah. Oh, okay. That side messes me up all the time. When
Yeah.
it comes to semester exam, start test, anything like that.
Yeah. So we have to know what the names of these place values are. And it's very similar. It's like a mirror image of the other side. So if this is the ones place, then this is going to be the tenths with the TH. And then the hundredths. And then the thousands. So everything on the right-hand side of the decimal has that TH. Then obviously you could think of this as the 10,000ths comes next. And the 100,000ths. And so on and so forth, right? Typically, we don't go out that far, like I was saying, because in our normal daily lives, when we're shopping or using money or doing any kinds of transactions, we only have 2 decimal places that we care about. But you know, if you were in financial markets, sometimes you go out more decimal places when you're talking about the value of some asset, whether it's cryptocurrency or a stock or something like that. You might go to the gas station and see that on their signage, they say gas is, I don't know what gas is right now. I just pay whatever it is, but it's, let's say it's $2.78, and then they have a little 9 in the corner. That's $2.78 and 9
But there's
cents,
also taxes.
and then 9/10 of a cent. Right? So those place values do exist. When you get into, if you're in science or engineering, you might go out 3 decimal places, and that's typically where we leave things off. In higher mathematics and in higher engineering, you might need more precision. So we need those other place values. Okay, but that being said, depending on what the problem asks you to do, what place value to round things to, that will determine what your final answer will be. Okay, so let's look at some examples. And we'll start off with simple examples and then hopefully ramp things up a little bit. So let's say we had the example 78. We want to round this to the nearest tens place. So what do I round this up to? I just sort of hinted at what we need to do. Well, this instruction that I've been given, round to the nearest tens place, is basically saying, okay, we're concerned about the tens place. So you could think about these as place values here, the ones place, the tens place. We care about the tens place. Another way you can interpret that is that it's asking us if we're counting by tens, 10, 20, 30, 40, 50, 60, 70, 80, right? And so on. Is 78 closer to 70 or 80? That's essentially what we're doing here. So when you're rounding a number to a certain place value, you're saying, okay, well, let's put this number between these two values that we used counting by the place value that we're interested in, tens. So on the number line, what that would look like is like, okay, we have a number line. I know that 70 is here and 80 is here. And you're asking yourself, 78 is like over here somewhere. Is that closer to 70 or is it closer to 80?
I'll say 80.
Yeah, it should be closer to 80. So we'll say that our answer is approximately 80, right? 78 is closer to 80 than it is to 70. Okay. The other way that you might have done it is said, okay, if we're interested in the tens place, you go over to your neighbor, and if that is 5 or more, you can bump this number up by 1. Okay. Both of those mean the same thing. But now if I gave you that same number, 78, and I said round to the nearest hundreds place, then what would you round 78 to? Anybody?
Hundreds.
Rounding to the nearest hundreds.
So it'd be 100, right?
Yeah. Yeah, and we can interpret these instructions the same way, right? We look at the place value that we're interested in, and we could say counting by hundreds. So 0, 100, 200, 300, and so on. Counting by hundreds. Is 78 closer to 0 or 100? And then you could, look at the number line. Imagine that you're starting at 0. You have 100, 200, 300, and so on. Okay. But 78 goes about right here. So we're not really concerned about the 200 or the 300. We're just looking at that space between 0 and 100. And then you're just asking yourself, is this closer to 0 or 100? And it clearly seems to be closer to 100. Okay. So then we could say that just rounds to 100. Another way you could think about it is like you have a friend and they owe you $78. And they, for whatever reason, they're just a big baller and they just have a wallet full of hundreds and they don't really care about the excess money, the extra, what would it be, $22 of no concern to them. So they just give you 100 and they say, let's just call it even. That 100 for them is close enough to the 78 that they're like, I don't care about the chump change. Okay, that's essentially what you're doing when you round. But rounding is something that we're gonna have to do when we do division, because sometimes when we divide, we get decimal numbers, and then Hawks might ask us to round to some place value. So we have to be prepared to do that, especially with these decimal places. Okay, so let's do some practice rounding and some practice dividing also. Okay, so practice with division and rounding. So let's say that I had 7/3, okay, and we want to divide that. And the instruction said round to the nearest thousandths place. Okay,
So for us to show the work, the 3 is out on the outside, the 7's in the inside.
yeah, exactly. So we would go ahead and do that long division, right? 3 is on the outside, 7's on the inside. Okay. Now, we could start our division off and say, how many times does 3 go into 7 without
That
going?
should be 0, correct?
Well, 3 is large enough that it can go into 7 a couple of times, right?
So maybe 1.
Well, 3 times 1 would be 3, right? Can we get a little bit closer to 7? 3 times something else?
2. It'd be
Two.
6.
Oh,
It would be 2, right? Like if I had 2 times 3, that would be 6, right? So we got close to 7 without going over. It's sort of like the Price is Right rules. Okay. But then when we do that, we have a remainder of 1 when we subtract. But we need to go to the thousandths place. So you just have to now throw some decimals in. So we have a decimal here and here. And we need to get to the thousands place, the thousandths. So we can count, this will be the tenths place, the hundredths place, the thousandths place, and that's how many zeros I will add, but I will actually add an additional one. We want to go one more place value out. Go one more place value out beyond what the question asks you, because we sort of need that neighbor. Okay. So I've added 4 zeros here. We're just going to divide until we have used up these 4 zeros. I'll go ahead and drop the 0, and we can start the division process over again. 3 goes into 10 3 times, because 3 times 3 is 9. That's pretty close to 10. We'll go ahead and subtract that. And unfortunately, we get a 1. We have another remainder. So we have to divide or drop another 0. Unfortunately, 3 goes into 10 again 3 times. 3 times 3 is 9. We can drop the next 0, end up in the same place with a 1 as a remainder. So we get 10 here. 3 goes into 10 3 times. And you can already see probably 3 times 3 is 9. We get a remainder of 1. We'll drop this 0 again. And then our final set of division, 3 goes into 10 3 times as a 9, and we can stop here. Okay, a lot of work. And it was just very repetitive. It is what it is. So our answer that we got so far when we did that division is 2.3333. Okay. But this problem is asking us to round to the nearest thousandths place. Okay. So we have to look at the thousandths place, tenths, hundredths, thousandths, and then go to its neighbor. And this is sort of like borrowing sugar. I always use this example. You're trying to make some Kool-Aid, but you're out of sugar. So you go over to your neighbor's house, and if they don't have enough sugar for you to make Kool-Aid, well, then you can't borrow sugar from them. Okay. And let me stop using my analogy now. What we do is go to the neighbor, but if that neighbor does not have a 5 or more, then we cannot round this up. So because this is a 4 or below, we have to just cross that out, and our answer will just be approximately 2.333, and that will be it. Okay. So the trick here is that we want to go to the neighbor, go to neighboring place value. And we're essentially checking for a 5 or more. If they have 5 or more, we can bump up our place value of interest. If it is 4 or below, we just leave this alone and ignore the rest of the place values. Okay, let's do another example. Let's do 49 divided by 5. And we'll round this one to the nearest whole number. We can think of that as the ones place. Okay. So I'll give you guys a minute. Write that one down. Use the long division. And what I want you to do is give me the exact value and then the rounded value. What should I get when I divide these numbers? Any ideas?
$9.8.
Yeah, that's the exact value, right? So we could throw this into our long division algorithm, 49. And since we want the ones place that's we're going to round to, we want to go 1 decimal place out beyond that. Okay. And we'll divide that by 5. So we say 5 doesn't go into 4, goes into 49 9 times, that's 45. We'll subtract that, get a 4, drop our 0. And then ask ourselves, does 5 go into 40? Sure it does. It goes in 8 times. So 8 times 40, or 8 times 5 is 40. We'll get a 0, and that terminates the process, right? So our exact answer is 9.8. But if we were to round this to the nearest ones place, or the nearest whole number, then what should my answer be?
Would it be 10?
Yeah, it would be 10. Because we look at our place value of interest is the ones place. And we look at the neighbor. And if that is 5 or more, we can add 1 to our neighbor. In other words, we'd say 9.8 is closer to 10 than it is to 9. Okay. So this rounded answer, based on the instructions given to us, will be our final answer. So you want to be careful there, because I've had students that have worked in Hawks and they say, you know, I'm very sure that the answer to this problem is 9.8, but Hawks keeps telling me that I'm wrong. And I keep putting it in, it keeps telling me that I'm wrong. Well, usually what happens in that case is either they've made some sort of arithmetic error, or they just didn't read that instruction that said to round to the nearest X place value, whatever the place value it wanted. Okay. So make sure that you're slowing down and reading those instructions so that you're not very frustrated with Hawks telling you that you're wrong when the instructions told you to round. Okay. So for rounding in general, just to leave you guys with a final note on rounding, your steps are that you want to go out one more place value further than the place value of interest. That is, you go one more out to the right. If they tell you the ones place, you'll look at the tenths place also. If they tell you the tenths place, you'll look at the hundredths place also, and so on. Okay. If the neighbor to the right is 5 or more, then round the place value of interest up, which is essentially adding 1 to it. Okay. If not, the place value of interest stays the same, and we ignore all remaining place values. On the right. Okay. I'll give you guys a little bit of time to write that down. Is anybody still writing?
Yeah, I am.
Okay. Does anybody have any questions or comments?
I'm good.
Okay, cool. Okay, well, to finish up our discussion of division, in chapter 8.4, there is a little bit about calculating the average or the mean value of a set of numbers. Now, this is something that if you were to go into college algebra, you don't see a lot, but if you are in a nursing track or required to take a statistics course, calculating averages is important. In fact, I think that calculating averages is important for all students because every now and then you'll want to calculate your average grade based on your homework assignments or based on your tests. This is how you would go about doing that. So the average, if I can spell, average or sometimes what's called the mean value sort of tells you the midpoint or some middle number that is in the middle of a set of numbers. So the average of a set of numbers is found by adding all the numbers in the set then dividing the sum by how many numbers are in the set. So this is something that you might have heard about, find the 5-day average for the temperature, right? A meteorologist or weather person might give you the 5-day forecast and they might say, oh, okay, the annual temperature for the year, the average annual temperature is higher this year than it was last year. Well, that's an average that they're calculating, okay? So let me give you an example that we can work through together. Let's say that we're thinking about temperature in Aspen, Colorado. So in Aspen, Colorado, the temperature for the last 5 days were, I'm going to write these numbers in a set. So let's say one day was 5 degrees, a -5 degrees Fahrenheit. We had a 7-degree day, a 6-degree day, a -7-degree day, and then a 14-degree day. Okay. And we need to find the 5-day average temperature. Okay. So when you're finding averages, it's a 2-step process. What we want to do is, in the first step, we will add together or sum all the numbers. So we need to take -5 plus 7 plus 6 plus -7 plus 14 and figure out what that is. Okay. So if we need to add these numbers together, you notice that we have some negatives and some positives. So we're going back to our addition rules. And remember that one of our properties of addition is that it doesn't matter what order you add things in. If we're purely adding, then we can add them in whatever order and it won't change the result. So what I would do is take the negative numbers first and add those together. When you're adding two negatives, you add their numbers, add their absolute values, and keep the sign of the number. So they're both negatives, so we're going to have a negative result. -5 plus -7 should give us -12. Just so that that doesn't confuse you any further, you might want to cross those numbers out because we're done with them. Okay. Then we can just add our positive numbers together. So we have 7 and 6, which adds to make 13. And we're adding that to our 14. So 13 plus 14 should give us plus positive 27. Okay. Okay, well, then we're adding our positive and negative, so we can think about that as take the larger number, which is the 27, subtract the 12. That gives us 15. We keep the sign of the larger, which is positive, so this stays at positive 15. This is our sum. Okay. But that we didn't just need to sum the numbers or add them up. We need to find the average temperature. So step 2 is divide the sum by the number of values in the set. So how many numbers did we have in our set of numbers?
5.
Yeah, there's a set of 5 numbers here. So we need to do 15, our sum, divided by 5, which is the number of values we have, and that will give us 3. So to interpret this problem, the 5-day average temperature is 3 degrees. That's our 5-day average temperature. I'll just put temp. Anybody still writing? Okay. Well, the last thing I'm going to throw at you is just a quick discussion of area. And this is section 6.3. And the reason why I just sort of throw it in at the end here is because area is fundamentally related to multiplication. But area is a concept from geometry that we're probably a little bit familiar with. If you went out to buy a rug, an area rug, it is a rug that
I'm not a big fan of area.
you said not a fan of area?
Yeah, because that's one of the problems I have.
Well, hopefully we clarify some of that right now. But area, if you went to buy an area rug, it's the area that covers the floor in some room, right? Or if you were to paint a wall, you would need to find the interior surface measurement to figure out how much paint you need to cover the entire wall. So area is a measure of the interior, and you might call it the interior surface of an enclosed shape or space. And area is measured.
Does that say enclosed or just closed?
It says enclosed
Oh,
in square units. Okay. So we can think about area as square units because, let's say, for example, I had a rectangle. And that rectangle had, let's say, had units of measure. The length and the width were 5 inches on this side and 3 inches on the other side. Okay. What I could do fundamentally, and this might be something that you might have seen when we talk about multiplication in grade school, is that you can break up this side into inch markers. So we would have 1, 2, 3, 4, and then this would be our 5-inch length, right? Where this is sort of like a number line. This is 0, 1, 2, 3, 4, 5. And we can break up or cut this rectangle up into columns where you just extend these lines straight up, or as straight as I can get them, okay? We can do the same with the width over here and say, if I started counting at 0 here, I could cut this into 1, 2, and then this would be 3 inches long. So we can cut this space into 3 sections or 3 rows, where now if I looked at one of these little grid squares, the little square on the inside has a length of 1 inch and has a width of 1 inch. And so if I wanted to count the interior of the whole rectangle to see how many of these 1-inch squares I have, well, I would count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So that's why we measure area in square units. Area is the sum of all the square units. And the area of this rectangle is 15 square inches. Okay. So in the last 5 minutes, I'm just going to throw the area formulas for the shapes that you're going to run into in the Hawks homework. And we'll run through some examples at the beginning of class tomorrow. Okay. So don't feel like I'm throwing you in the deep end. The shapes that we're going to run into are triangles. And typically a triangle will be expressed like this, where we have some dashed line here in the middle that gives us a measurement of the height of the triangle. So the height of the triangle is represented by the letter H. And then the bottom of the triangle, which is typically sort of perpendicular from the height, is the base. We represent that by a B.
So it'll be H and W, I mean, H and B.
Yeah. So the area for the triangle is going to be base times height divided by 2. Okay. Well, again, we'll have some examples next time. I just want to give you these formulas. For a rectangle, we typically call the sides length and width. So we call this L for length and W for width. And the area of a rectangle is calculated just by multiplying length times width. For a square is a special kind of rectangle whose sides are all the same. So if I know one of the sides of the square, because it's a rectangle, then the area here should just be one of the sides times the other side, or we could think of that as exponents as the side squared. So one side times the other side, and you'll get that area. Then finally, we have two other shapes. There's a parallelogram. And the parallelogram sort of looks like a slanted rectangle. And for this one, we just need the base of the parallelogram, so B, and the height of the parallelogram. The area will be equal to the base times the height. And then the trapezoid which looks something like this, is a little bit more complicated because we have one side, which we might call the first base. The bottom side we might call base 2. And then we need the height also. So H. So to find the area for a trapezoid, we need to multiply the height times, you add the bases up, base 1 and base 2. And then you divide all of that by 2. Okay. So again, I know that I ran through those formulas and just sort of threw them at you. We'll look at some practice problems calculating area next time before we start talking about fractions. Okay. So with that being said, and a minute to spare, you guys are free to go. If you have any questions, you guys can hang back and chat. Otherwise, I will see you tomorrow, same time, same place.